Language modeling is a very important part of modern machine learning, and understanding it can also be useful outside of working with language because language modeling was the area where the most important parts of very successful AI technology started, and it has then been expanded to also work with other things such as images and so video and so on. So many people have probably heard of the transformer, and the transformer is a kind of architecture for a neural network which allows for a specific kind of machine learning. And it can be used for many different things. It can be used for creating certain things that are called next token predictors. So there's many ways to talk about language modeling. The most intuitive way, at least as a bridge from understanding maybe what it means when we train a neural network to predict the label for an image with some digits, would probably be next token predictors. So let's just say here we have supervised learning. In um, that domain, you can imagine you get some image. It says 3. You want some kind of magical AI thing here that gives you out a probability distribution for the digits 1, 2, up to 9, where you have a quite high probability on 3 and less on the others. And the way that we think of this is that there is a data distribution called p x comma y, and we're interested in the conditional distribution p of y given x. It's a data conditional distribution. This is given the c and x, what is the probability for each of the labels. So given an x, it could be 28 by 28 matrix of zeros and ones. Give me a list of 10 numbers summing to 1. List of 10 positive numbers summing to 1. The conditional data distribution is a way of thinking that out in the world there is a distribution over images and labels, and some images might be a bit hard to see. I don't know if it's easy to imagine. Maybe something like, or if you went all the way here, then you were maybe think it could also be a 0 or something. So it's a 3 or a 0. So there can be some probability associated with it, but it does not need to be deterministic. It could be that out in the world there was always a right answer, and then you just have all the mass on 1 and you just have 0 here for the other digits. But in any case, that's how we think of it. It's the way you think of it in statistics also. Often, like, you take some samples, you measure some heights or something, and you view them as samples from some underlying distribution that's kind of in a way infinite. And then that's the first thing to understand about supervised learning, the idea that it's a data distribution. Then the second thing is we view finite data sets as a finite concrete set of samples from data distribution. This means that MNIST, what is MNIST? Example given, MNIST is maybe 60,000 pairs like this. You have an image of a 6 and then a 6. You have an image of a 7 and it says 7. You have an image of a different 7 like that, and so on. These are viewed as being samples that are, in a way, instantiation of random variables up to n of 60k, and they are viewed as kind of samples from some p xy, some distribution. Then the third thing is we want another probability distribution called the model Q of data distribution P. So we want that there is, for an image, an ability for us to tell 10 numbers that sum to 1 that are positive that act as a good estimate. This can be good or it can be bad. Bad Q would maybe say I have an image 3, I put it through and I get something where it thinks it's quite likely that it's a 0 or a 1 and actually does not think it's 3. Or I can have a good one, Q, it goes through and it takes high value on 3 and low on the others. What do we measure good or bad to with respect to P? P is the truth. P is the true distribution. 4. Measure goodness of model Q by how not surprised you get when observing data from true P. So if you see this thing in the world and you have very high probability, so Q, the value assigned to the label 3 given an image 3, if that is 0.99, then you're not very surprised when people tell you that it is actually 3 that's the right label. So what does this mean? It means someone called Alice has this pair. She gives Bob the image and Bob says, I have different probabilities. I have high on 3, I have low on 2, etc. And these are all my things. And then Alice says, great, now I have your list of 10 numbers and let's see what you thought about the actual true label 3. Oh, Bob, you said 0.99. And then Bob says, yeah, I'm not that surprised that it's a 3 because I also thought it was a 3. Surprise is the minus logarithm of what Bob thinks, Q, of the label given an X. Surprise, and this is the 3 and this is the 3. So we are trying to minimize the cross-entropy where we sample X and Y's from our true world and we evaluate how surprised Bob is getting. And this is on average. And we estimate it by having a bunch of samples X, I, Y, I in a data set, in a finite set D, and we measure the surprise. This is called Monte Carlo, if we want to be a bit pretentious. So then the fifth step is make a neural network that allows for representing Q, Y given X. That means given a specific image, I want to be able to output 10 numbers that are positive and sum to 1 for the probability. And the way that I can do this is I can take the image 3, I can view it as a 28 by 28 matrix of zeros and ones. I can turn it into a 28 by 28 matrix of values, so it's kind of an X in R784. And now I can make some function that maps from R784 using to R10, where I ensure that they are positive and sum to 1. And one way of doing it, this would be with an MLP, where I compose a set of layers, sequence of layers, where I use one layer is an affine transformation. I have an input vector x, it might be this existent vector. I multiply it by a matrix, this maps it to another vector with some dimensionality. I add the vector, and then I maybe finally affine plus activation function. An activation function could be the value, which is max of 0 and x, so it looks like this. And I apply this to every entry in the output vector, and therefore I also view it as, I could also write value. No, I will actually do it like this. I will say phi. Phi goes from R of D to R of D, and it's a function that applies value to each entry in the input vector. So one layer is phi of A x plus b. So this is a layer. Maybe I could write f of s, where s will be a specific layer, layer s. And for I have an input vector x and I use a matrix, and this is the matrix I also associate with a specific layer, and the bias vector I associate with a specific layer. Great. And then I would maybe do function composition. I take an x, I pass it through this, it outputs a vector. So let's just write this f of s. It maps from some dimension to another dimension, r k. And if I then ensure that they match the different f of s's for the different s's, I can write my MLP of x. It's kind of a functional composition. So I compose f1, it depends on the notation, of course, f composed with g. I think I'm just gonna define, like, maybe, like, usually we don't do it like that, but like, let's define our own operator. It's called this, and it's f of 1, f of 0, s0, so we go s is equal to 0 up to s, f1 all the way up to f of big S of vx. So this just, by this I mean I apply the first layer on the vector, then I apply the second layer, then I apply the third layer, and the fourth all the way up to f of s. And it gives me some output vector. And in the last layer, so I can either view it as having a last layer. I do not want this phi, so I could also think that there is an output matrix A here. I'll actually write it as E out, I think. E out. And this E out is a matrix that is like 10 digits, 10 rows, and whatever may be some kind of k columns. There's k columns. So when I multiply this, then my MLP, it will go from RD, maybe 784, let's write this, 784, to R10. And now I have a vector. It's called, let's call it set. These vectors are, if I just have a matrix, they are not necessarily non-negative and not sum to 1. So these are also called logits. So lastly, I want some kind of operation that does this, softmax. Softmax is an function. It takes a vector in Rd, some dimensionality, maybe R10 in this case, and maps to the same, but it ensures that it sums to 1 and are non-negative. How can we do this? Well, just thinking about it, exponentiating it will turn it positive. So what I write here is y is equal to softmax of some vector x, and the way I define it is that yi, the ith entry, maybe each digit, is exponentiated version of the corresponding entry. But we also want to normalize it so that it sums to 1, so we divide by the total sum after we have exponentiated them all. Great. So we can also think that this just means that yi is like proportional to the exponentiated xi, and we could also have some kind of temperature that determines, like, this is shared for all, that kind of says how should I exactly use, which like base should I use. If I have a higher value, then I will change like how much importance is given to the values that have the highest value in the vector. But in any case, we now have something that is a vector y that sums to 1 and is positive, so it's a probability distribution, probability mass function, and we can kind of use this here at the very end. And then we have a good neural network. So that was a bit of a long view of supervised learning, but this is the context at least that we can use, because now then let's see what number we had, 5. So we make a neural network that can output a distribution, and 6 we get the gradients, So if we do it right and use matrix multiplications and all these things, then this function is differentiable. So a matrix operation addition is kind of differentiable. ReLU functions, they have kind of this point here where they're not completely differentiable right at the point, because the derivative from both sides do not agree. But like if we kind of just ignore and think it will never hit that exact point, then we can kind of think that the gradient here, the derivative is 0 and 1 here. And or we could just have used a different function. So other functions are differentiable. ReLU is like just the easiest thing to think about. And therefore we have this thing called AutoGrad. It's a kind of software that exists in PyTorch and in JAX, that if you define your Python function with these matrices, multiplying it on each other, applying some ReLU functions, etc., all these different things, and softmax, all these things, then you can have a derivative. And it's a bit of an intuitive thing, because usually we think that we want a derivative with respect to the input. But in this case, we have all these matrices, A and B, and these, and we also have the E out here. These matrices are determining how the function works, what it actually outputs. So we can actually see the this neural network as being mapping from RD, but it also has this kind of weight, all these parameters, and we would maybe do a big omega here to, no, I think I want to rather use W, a big W, to some like R10 or something. This means that we could think about, if we fix the inputs, then we have kind of a function that goes from the weights to the output. Let me just think if we should continue a bit more all the way to the loss. Yeah. So let's go a bit back. We now know that Qy of x, it's in a way the same as the output we give to our network, but as I said, there are some kind of weights, and I will write them here. If we think of f as kind of an architecture, it can take some parameters, and thereby it also computes an input, and then it computes a value. and it outputs a full distribution, and this is also a full distribution, and often you would then write this as like just having some kind of dot here. So the distribution is this whole full thing. And this means that our loss function, we were trying to minimize this HPQ. It is being approximated as 1 over n of the expectation of the minus log, not the expectation, the sum, minus log q yi xi. And q here is given by f. So we could maybe write something like 1 over n minus log, and then we need to talk about the output here. So I will just say that it outputs a vector q. Is this going to be too confusing? I think it's okay. Q, and then we have an entry here, and this is the digit. So let's think about it. Yi can, for example, be an xi. It could be xi is going to be an image, and yi is going to then be a specific value, right? It can be 0 to 9. So it's actually valid to just write yi in here. The yi'th entry in this output vector that sums to 1 and are non-negative, so it's probability distribution. This is exactly what we want. So if I will just write it in different ways, maybe some way is better than other. We could also think that we have this whole thing here. What does this give you? This gives you a vector. This is q, and then you take the yi'th entry in it. So at least now we see that we have a function L, and then we say I actually care about the parameters theta. The parameters theta is a function of a lot of things. It's a function of the data that I use, and it's a function of the parameters. And the parameters theta, it's kind of just the set of all these, like A1 all the way up to AS, and B1 all up to BS, and then the E out. These are all the matrices and vectors that determine exactly how we predict, and it changes how surprised we are, and it changes this loss function. We want it to be very low. And the way we can then do this is that these PyTorch AutoGrad frameworks, they allow us to compute the gradients with respect to the weights. So it's not really a vector, it's all these things, but we can change them in a tiny way, and it will change the loss. So this is the gradient. And then we are at 7. Optimize the loss. By using an optimization. So we want to find, ideally we want to find the best thing that kind of minimizes the loss. The one that is closest. Ideally we would get as little surprise as possible. And the way we do this is then with some optimization procedure. One way is that you think that we have this function. It's not a function like this, but this is a bit bad, it's a bit too. This is the minimum. If we only had one parameter, this would be the minimum. we could be here. If we take the derivative here, we could go in this direction and we increase, or we could go in the other way and we decrease. The same way in high dimensions, if we kind of go tune all these parameters a little, we get this, we use this approximation, a kind of tangent, or like a first order approximation of the function, and we minimize that in a tiny bit and we get to another point, and we kind of continue that until we reach a good value where we are very low, where the gradient will be or the derivative will be almost zero. So the way we do it is we say I start at time 0. So what is time now? It's like we have a sequence of maybe I think it's okay with using time here. So phi t is like a sequence phi 1, 0, all the way up to some very point, and then we stop and we use this final thing and we hope we end here. How do we do it? We start by taking phi 0 as a random variable from some distribution p of theta. This could be normally distributed values, and then we update phi t is equal to some kind of function of what of the previous one. I will use another because I used f a lot, so let's call this u. U, it takes the current parameters and it somehow takes the gradient with respect to parameters of L of phi of t minus 1, and it gives you the next one. Some way of moving in this direction by where we are currently and what the derivative is. And many examples exist. The most simple one is to say that we use our current one and then we go in the negative direction of the gradient using some little small step size. It's called the learning rate. And then we multiply by the gradient with respect to the parameters of this thing. Gradient descent. And let me just check that everything works here. It seems to work. Okay. Now, once we have this, we say, but we have a huge data set. Data set, we cannot just sum. We cannot just sum over all this full data and compute the output for all of it, and then compute the gradient, and then do a little step in the right direction that goes to a lower L, and then do it all again. So we do stochastic gradient descent, where we say this gradient here it is, what is it? It is the gradient of all this 1 over n, and what is this? This is kind of already an approximation to the gradient of the HPQ thing, where Q depends right on the parameters, and therefore we can already say, like, we were already approximating h using a number of samples, so we could also just use a smaller thing. So we're gonna do mini batches, or just batches. It's the same word in this context, at least. So we say, I'm gonna take b different pairs, b pairs. So I'm gonna say, what if b is 3? I'm gonna take this image and this pair and this image and a wrongly labeled one, maybe. It was actually a 7, but they thought it was 1. Okay. And now I'm gonna just use this. So I'm gonna say h pq is roughly 1 over 3, 1 over b here, of the sum of this. So yeah, I hope you get the idea. I write q theta because then the q kind of depends on the weights of the neural network, of yi xi. And now xi and yi are not from the full dataset, but it's just from this tiny batch dataset. And I'm gonna use this in one round and compute the gradient of this. So I'm gonna compute the gradient of the loss. Theta is like approximately the gradient of all this. And that would be, then the gradient then would be 1 over b, and then I kind of move in here and take the gradient of this. And actually we could, it does not make sense to say where we start, because now we're starting to use the chain rule inside and qi and so on and expand it, but this is what PyTorch will do for us. So we could just say that we actually already compute all this and then we take the gradient. But in any case, we now have some method to move, because let's think about it. Let's write a little algorithm pseudocode. What do we have of the different steps? We have given architecture f, some kind of weight space. I was a bit unsure what I should use. Architecture weight space omega, initial weight distribution p of theta. This could just be a kind of normal distribution, and then we have a data set d to n, and the batch size b, and what do I have? A learning rate alpha, and a and maybe number of steps. There's of course always some details that we are leaving out when we are making pseudocode, but we say for step I in range n steps. So it's a bit Pythonic pseudocode here, n steps. What are we going to do? We're going to get a batch and we're gonna sample a batch. Random sample of B pairs from our dataset D. We are gonna before this we are gonna say phi 0 is gonna be sampled from P0. Then we're gonna say compute the cross entropy H PQ is equal to 1 over B, as we said, minus log Q. I'll actually do it now with the old notation that I did before, just to avoid the Q now. F of xi and theta. I'm just going to remove this. I say that this is theta always, theta. And then I take the ith entry. And once I have this, then I say grad theta h hat PQ is equal to just compute with Jax, and then I say theta is equal to theta as it was minus some alpha times the gradient of the estimated gradient of the cross entropy, and then I continue when maybe I print the loss, print the cross entropy, and once I have this, then I will see if loss H PQ theta not falling so much, stop. So this is just roughly what we have. Now, once we have all of this, we are ready. This turned into a lecture of supervised, but I think it was better than what I have done previously. So now we start then to get ready for language modeling, because I think, we can actually compare it here. So if I move this up here, I will say, what is it that we now have? We have a data distribution. What is this data distribution? It is a sequence of texts. And we will start in an easy way where we assume, a thing that's quite unrealistic, we assume that there is some length T. It could be maybe 4K words. And now we have some set X, large set, and it is all words in dictionary. So it's quite large. Maybe it's 100K words or something. It could also be in a different kind of thing, but this is just for simplicity now. We just think that we have these sequences of this, and therefore we write x1 to I'm actually gonna just imagine first, imagine then some sequence like this, it's essentially in the set x to the power of t. The Cartesian product is some sequence, and we will think that it could be, example, high there, and then we just have some white space all the way to t, because in this way it will be a bit simpler for us to talk about. We could also talk about how it just goes on for infinity, or not infinity, but like arbitrary length, but this is going to be simpler. So now this is the data distribution, in the sense that we now have a probability mass function, not over x1, x and y like this, but x1 to xt. And most importantly, by the product rule, we can view this. Oh, now I don't have any power left, so I'll stop and continue later. Or do I? Can I just draw here? Is it? No, it will not work.